We started last Wednesday talking about the relationship between the x values and the y values here. We determined that the relationship between the numbers 3, 5, and 15 is that 3 times 5 equaled 15. 3 and 5 are both factors of 15. And that the relationship between the y values or the log values was that if you add them together, you get the larger value. So 0.477 plus 0.699 was 1.176. And we also determined that because they had the same base, that meant that we were dealing with the exponents. So adding the y values of the logarithmic function was the same thing as adding the exponents of the exponential function, which makes sense because they're inverses. And then we talked about predictions, kind of mixing and matching, using some other values for those as we went through. So we actually finished talking about, we talked about the first law, or the first property of logarithms, the product property of logarithms, and that's because we talked about why it worked. And the reason why it worked is that if you have the same base value in a logarithm, that means you have the same base value with your exponent. And if you have the same base value with your exponent, that means you're allowed to add the exponents, which ends up being the product of the logarithm that you're dealing with. So if you have, for example, we did some substitution. We said we're going to let x equal log base b of m, which meant that b to the x power is equal to m. And we did the same thing with y. We said log base b of n is equal to y, which means that b to the y power is equal to n. And so if we were to multiply those two things together, b to the x times b to the y, that would be the same thing as multiplying m and n together. But if you multiply two of the same bases together, you can just add the exponents. And so once we got to that point there, we were able to substitute a little bit because, well, we first converted to logarithmic form. So we said if you have log base b of the argument mn, which is here, you're going to get the exponent, which is x plus y over here. And then once we got to this step here, we said, all right, I've got log base b of m times n, which is equal to x plus y. If that's x and that's y, that means I could have just added the two logarithms together to get the product of whatever m and n was, or log product of whatever m and n were. And the same thing worked with division as well. Division of exponents is the same as subtracting the exponents, basically. So we also worked with that. So we're learning some laws of logarithms here. So if you subtract logarithms, that's the same thing as subtracting exponents with the same base, as long as you have the common base with those logarithms. Now, we got to this example here, and at that point, we kind of paused things and said, okay, we're going to go ahead and hold off for a second. Now I'm going to write something a little bit different once we get to right here, and I want to explain what's going on with this one here. So basically, we're saying, all right, as long as we have the same base value, which we definitely have the same base value, and we have the product of these two things in here, you can split them apart into the sum of two logarithms. So if you take log base 5 of a squared, and you take log base 5 of b to the 7th power, you can add those together and get to the original. Or because they were already together, we could expand them and write them as a sum of two logarithms with the same base. And so that's where we ended up with last Wednesday. Now, this could be an answer, but I'm going to go ahead and kind of circle back to something we were talking about with one of our natural logarithms in our warm-up, and that is, there is a slightly simpler way. There's a slightly simpler way to write each of those. I'm going to use this one right here as an example. So, real quick, if I were to write log 5, I'm just going to give myself a little space up here. So go and draw an arrow to log 5 of a squared real quick. Log 5 of a squared. I'm going to show you something off to the side up here, and it's going to kind of speed things up in the end, but I want you to see I don't want to show you the shortcut yet. I want you to understand why we're going to write what we're going to write. So up here, we've got log 5 of a squared. So I'm going to give myself quite a bit of space. So log 5 of a squared. What would that look like in exponential form? What would this look like in exponential form as opposed to logarithmic form? What's our base? 5, okay. We don't know the exponent, so that's what we'd be figuring out. So that would be x. And that would equal a squared. So it'd be like 5 to the x power equals a squared, right? That's basically what that would be as. So this would be 5 to the x equals a squared. But we could also write that as a times a, right? A times a. So 5 to the x equals a times a. Okay. So think about that for a second. A times a is a squared, which means that if we let's go down here for a second. Would you agree that that would be the same thing as writing log base 5 of a times a? Because a squared is a times a, right? Everybody good with that? Now, we also said that logarithmic addition works if you have two things multiplied together here. So we could use the rule, the product property for logarithms on this one, and write this as log 5 of a plus log 5 of a. Because if you have a product here and you have the same base, this would be the same thing as that. We just talked about that on Wednesday. It was a quick reminder down here, but we just did the same thing here, right? A squared times b to the 7th splits it apart into log base 5 of a squared plus log base 5 of b to the 7th. So we can do the same thing again here. A squared is a times a. Log base 5 of a times a would be log base 5 of a plus log base 5 of a. Everybody cool with that? We're just using the product property again. Are there any questions about that? If you have a product here, you can add the logarithms. How many of these are there of that exact same thing? Log base 5 of a and log base 5 of a. How many of those are there? 2, right? There's one here and there's one here. So we could write 2 log base 5 of a, because there's 2 of them. Which means that 2 log base 5 of a equals log base 5 of a squared. So there's a quick way to make this happen, because if you think about what happened to the exponent from here to here, where did it go? Went to the front. But now it's a coefficient of the logarithm. A coefficient of a logarithm is the same thing as an exponent of your result or of your argument. So down here, we could rewrite this as 2 log base 5 of a plus what? Use that same logic with this next one. How many log base 5 of b's do we have over here? 7. So that would be plus 7 log base 5 of b. Because as you add exponents to your argument, you're adding coefficient values to your logarithm. All right. Any questions about that before we continue? Because this is an idea that is going to be really helpful and really useful. I think your light's on. So really helpful, really useful, but it's important to know why this stuff works, because the better you understand something, the more likely you are to remember it, and you won't even need to remember it because you'll know how it operates and how it works. And so it'll be less to do with like memorizing something and more to do with understanding something. So with this next one, do we have multiplication or division inside here? Simple question. Division. And so are we going to use the product property or the quotient property? Quotient property, yeah, because we have a quotient here, which means we're going to use the quotient property, which means we're not going to be adding logarithms, but instead we're going to be doing what with the logarithms? Subtracting it, yeah. So this will be ln of 25 minus ln 3. Now, is 25, and this is where things are going to get, I'm going to start asking some extra questions here. Can 25 be written as a perfect square? Yeah. Or factors in general. Is 25 a prime number? No. What times what equals 25? 5 and 5, which is 5 squared, right? So would you agree then that this would be ln, keep writing ln and n together, ln of 5 squared minus ln of 3. Everybody okay with that? So what we're going to end up doing is we're going to end up writing everything in its prime factorization in terms of the numbers, the arguments. Over here, there were no arguments here. B and A, those are just variables, so we don't know if there's factors or not. But over here, we have actual numbers. 25 has factors of 5 and 5, which is 5 squared. How could we rewrite ln 5 squared using what we used over here? It's the same thing as what we did with the log 5a squared. What could we do with the ln 5 squared? If you're not sure, I'll just go ahead and do another arrow right here. ln of 5 squared is the same thing as ln of 5 times 5. Everybody okay with that? 5 squared is 5 times 5. And that means we could use the product property with this portion of the problem and write, did it again, ln 5 plus ln 5. Using the product property for logarithms. How many ln 5s are right here? There's 2 of them, right? So this would be 2 ln 5, which means that is 2 ln 5. So the shortcut here is, if you have an argument that's being squared, that exponent, or not even squared, but if that argument is taken to an exponent, that exponent is how many times you are adding the logarithmic form together. So this is going to be 2 ln 5 minus ln 3. You can basically just take that exponent, put it in front of your logarithmic form if it's being squared, and then rewrite it like that. Are there any questions on those first couple examples before we take a look at some more? There's a lot of little detail that's actually happening in between here and here. That's this stuff over here. You don't have to do that every time, but it's important to understand that that's what is actually happening. Okay, I don't see any hands up. Let's turn the page. A couple more examples here. We're going to try A together, and then I'm going to have you try B on your own. So here we go. Log base 7 of r cubed t to the 4th divided by v. So are we going to use the product property, the quotient property, or both? Both. Yeah. Both of them are going to be used on this one because I see product property on the numerator and then I see quotient property from the division. So let's go ahead and just separate this all out real quick. We're going to get log base 7 of r cubed plus log base 7 of t to the 4th minus log base 7 of v. Any questions about that before we continue this process? The two on the top are being multiplied, so we add those logarithms. The one on the bottom is being divided, so we subtract that logarithm. It's the same as using exponential rules, except we're using them with logarithms as opposed to just using them with exponents. How could we rewrite each of these two without having exponents? Three log 7r, good. Plus, what's the next one? There you go, 4 log 7t minus log 7v, because there was no exponent with that v, so that one stays the same, log 7v. Nice. So, took care of that one. I would like you to try B on your own. Just keep in mind that there could be factors. And when I say factors, I want prime factorization. If there is a number that can be factored out, I want you to factor it out, and I want you to use prime factorization to do that. You see the prime factorization here? 225 turns into 5 times 3 times 3 times 5, or 3 squared times 5 squared.
The 15 squared, 55.
Yeah.
You have to put the 15 in front of the
No, because we're going with prime factorization as opposed to just sum factorization. So prime meaning break it down to the prime numbers that are factors of this number here, all the prime numbers. So this is going to be ln 7. Hopefully we had that part. Minus, hopefully we had that part. Hopefully you had this first part. ln 7 minus ln 225. Which is going to then give us minus ln 3 squared minus ln 5 squared. Why am I subtracting both of those? And even though it's the product property being used on the denominator, why are both of those minus? Why is this not a plus right here? Because they're being multiplied together, which would imply the product property. So why Why the minus there as well? Because we're going for the prime factorization. So like 15 is not a prime number. 15 equals 3 times 5. So if you can continue to factor that number down into smaller numbers, keep doing that. It's kind of like, I don't know, kind of like writing something in simplest form for a fraction. You keep reducing it until you can't reduce it any further. Same thing with prime factorization here. But who can tell me, why is this a minus instead of a plus, even though it's the product property? What if I rewrote it like that? Would that make any more sense before we just wrote 2 minuses? Does that help? See what's going on here? Because even though the denominators are being multiplied together, which means we're using the addition here, that is still the denominator. Both of those are part of the denominator, which means that negative distributes to both things. Which means we've got ln 7 minus ln 3 squared minus ln 5 squared. That's why it's 2 minuses down there as opposed to just 1. So I definitely skipped a couple of steps. So I went ahead and filled those in. We're 1 step away from an answer now. Who can tell me what the answer is? Next line is the answer. What are we going to write? Yep. We're going to keep the subtractions. How can I rewrite this without the exponent? There you go, 2ln3, and then minus
5.
Yeah, 2ln5. Nice. There we go. That looks like 21n5 and 21n3. Those are L's. That is what we should get for part B. You don't have to write all those steps down. Like if you get to the hang of this pretty quickly and you can start working through these without writing out that much, I'm fine with it. I just like to show the details, at least for the first couple examples that we do. All right, now we're going to go the opposite direction. By the way, going the opposite direction is going to be more useful in the long term, but it is good to be able to work both ways through a process. This particular direction, going from simplified to expanded, is, in terms of usability, not as useful, but it is good to be able to understand why. Now, going from expanded form and putting things together in a more simplified form is definitely going to be a more useful thing. So I see addition and subtraction, which means I see both product and quotient property. And I see numbers in front of each of the first 2 logarithms. So that means product property as well. By the way, or the power property rather. So the power property is one that we didn't really, I mean, we have gone over it, but I didn't explicitly show this to you. That's what we've been using to move down the exponent in front of the logarithm. So the power property takes the exponent with a logarithm, puts it in front of the logarithm, or opposite direction. If you start with a coefficient with your logarithm, that can turn into the exponent of an argument, which is what we're going to do on the problem that we're at right now. So that 4, this coefficient of 4 is going to turn into an exponent with an argument of n. So we're going to have log base 4, m to the 4th power, plus log base 4, n cubed, minus log base 4p. So we're putting the exponents back with the arguments, as opposed to having them written as coefficients with our logarithm form. Let's just focus on these first 2. How can we write those 2 as a single logarithm using the product property? How can those two be written as a product of two logarithms using log only once? I'll go ahead and start. Log base 4. What comes after that? Multiply together the arguments. What do you get? Not going to get regular numbers for this one. Multiply the m to the fourth is one argument, n to the third is the other argument. Multiply them together. What do you get? Yeah, and it's m to the fourth n cubed. Yeah. We can't multiply them together because they're not the same base. Yeah, so it'll just be m to the fourth n cubed. And I'll put those in parentheses just because it's getting a little bit more expanded. And then we're going to have minus log base 4 of p. What do we do to incorporate the subtracting of this log base 4p into this single argument over here? How do we incorporate this over to here using the quotient property for logarithms? Being subtracted. Well, we added the addition of logarithms turned into multiplication. So the subtraction of logarithms turns into division. So the answer to this is going to be, here we go, log base 4, m to the fourth n cubed over p. Grouping those together, we get that. Yes. All right, questions on A? All right. Let's try B. Take the coefficient, turn it into an exponent. What does that give us here? ln 2 to the third power. Good. Let's write that down. ln 2 to the third power minus what? ln 5 squared. All right. What is 2 cubed? What is 2 to the third power? 8. So that's going to be ln 8 minus ln what? 25. Subtracting logarithms looks like what when we write it as 1? Division. So that's going to be ln of 8/25. That's the answer to that one. Try A and B at the bottom on your own. Give those a go. How we doing with the notes back there?
You know, it's look like the fraction. That it is, but you put a file.
If there's subtraction, subtraction means fraction. There's a rhyme. So yeah, if they're being added, then you're going to multiply together the arguments, but if there's subtraction, you're going to divide the arguments. So for B, you're just going to multiply together all the arguments, which are all regular numbers. And so by the time you're done multiplying together the arguments, you just end up with 98. Because this first one here would be ln 7 squared plus ln 2. 7 squared is 49, and 49 times 2 is 98. That's ln 49 plus ln 2, which gives you the ln 98. Are the questions on either A or B? Are these properties starting to make a little bit more sense in terms of how to use them? Sometimes there's multiple things to do in a problem, so good to definitely see a few different types of examples here. All right, does anybody need more time here before we go to the next page? We'll try to get through maybe one more page before we're done today. We got 13 minutes. We'll keep working on this lesson again tomorrow, though. All right, here's our first application. So this says the pH of a solution, which I am led to believe is something to do with science. I don't really science much. So, you know, for those of you doing any sort of like chemistry classes, this is probably something, has anybody seen this notation before? The H with the plus exponent, I don't know what that means. Concentration. All right. Measured in moles per liter. What's a mole? Any chemistry folks here? No? Okay. I have no idea what this is talking about. Anyway, I can do the math though. So the pH of the solution is a measure of its concentration of hydrogen ions. This concentration, measured in moles per liter, is written as H exponent plus. I don't know how to say that. And is given by the formula. The pH level is equal to the log of 1 over H plus, H to the plus. What is the concentration of hydrogen ions in the acid rainfall? So we are solving for H plus, given a pH value of what? 4.5. Good, because it's acid rain. So let's just say pH equals 4.5. So now we're solving for H plus, and so that's going to be 4.5 equals 1 over this H to the power of plus. I don't know. So, oh, sorry, log. Nope, I'm going to rewrite that. That's terrible. Okay, 4.5 equals log. And then I'm going to put that in parentheses just to give us a little bit of a better idea, because this is kind of how we've been looking at things here over this unit or this lesson. So how could we rewrite this? Yeah. So we're going to get 4.5 equals log 1 minus log H to the plus power. No. What does this equal? What does log 1 equal? What does that mean? What does log 1 mean? Who can tell me what that means? What base value? There's no separate base written. What's the base? 10. This is the argument. So 10 to what power equals 1? 0. This equals 0. Log 1 is 0 because 10 to the 0 power is 1. So that's going to be 4.5 equals opposite log h plus. By the way, we're solving for h plus, okay? So that means we need to get this logarithm isolated first. So we still need to get rid of that negative. So if we divide both sides by a negative, that'll be negative 4.5 equals log of h plus. So now we're in a situation, take a look. Now we're in a situation where we can actually rewrite this in exponential form. Are there any questions as to what we've done so far? That h plus is just a variable. Like that could be x for all we care. In fact, if you want to write x instead of h plus, I'm fine with that. Just make sure you reinsert that h plus at the end of the problem. Any questions on what we've done so far though? Everybody okay with log 1 equaling 0? Okay, let's keep going then. Let's write this in exponential form. What do we get? We're writing it in exponential form, so no more log. What's our base value? If there's no base written, what's our base? 10. So that's going to be 10 to the negative 4.5 equals whatever we need. So whatever the concentration is going to be 10 to the negative 4.5, which would be like between it'll be between 1/10,000th and 1/100,000th. So it's going to be a very small decimal number. In fact, yeah, let's write it. Let's see, 1 and then 2, 3, 4. So 4 zeros. And then 316. Everybody getting that? 3.162277766 e to the negative 5. E to the negative 5 means 10 to the negative 5th power. So basically, take your decimal and move it 5 spaces to the left, and then fill in with zeros. So that's 4 zeros. So that means that h plus is approximately 0. Here we go, 4 zeros. 1, 2, 3, 4, 316. That is the concentration, concentration of hydrogen ions in moles per liter. Gonna write that, moles per liter. There we go. Whatever that means, that's what it is. I don't know. Let's do another one. Let's do orange juice and then we'll be done for the day. So, same problem, except this time the pH is 3. Which, I don't know about you, but I can just tell you the answer for that one. It's set up the same way, which means your exponent's going to be different. That's the only thing that's different. I'm going to give you 15 seconds. What's the answer? You said you were taking notes. Where? Yeah, that's good. Because the only thing that's different about orange juice versus acid rain is the pH level. All this math works exactly the same. It's just the value for pH is what we're going to swap in for the exponent as opposed to that value for pH. So what's the answer?
10 to the negative 3.
Which is? You're right. 1/1000 or 0.001. Yeah. Because the only thing that changes is the 4.5 turns into a 3. So if you get H plus by itself, that would be 10 to the negative 3, which is 1/1000 or 0.001. It's the only difference there. All the algebra, all the logarithmic changing, that's all the same. Nothing about that changes. So that would be pH equals 3. So moles per liter equals 0.001. There we go. Okay, we are going to pause here for the day. I'm going to get you your assignment. I don't think have I handed that out yet? I don't think I have. Okay, so I'm going to get that handed out to you. We will finish these notes. I think we'll finish them tomorrow anyway.